So I really hope so. I have tried to keep it very basic, the whole talk. Students who are joining in from first and second year, I hope some of you are. Um, yeah, I think you will find it more or less followable. And anybody, if you have any questions, you can stop me anywhere during the talk and ask me questions. So yeah, I think we'll begin now. And so everybody, whether you're from a theoretical background or an experimental background, you'll be able to follow the talk. I will try to keep it as basic as possible. So my thesis work was on fabrication of superconducting thin films and Oneprobe Tc measurement. Right. So, right. Okay. So what are thin films? So they are basically very thin layer of any material. It can be a conductor, a semiconductor, an insulator, ranging from micrometers to nanometers. And thin films have actually revolutionized the electronics industry with PCBs. So PCBs are used for making very compact electrical connections. So you can see this PCB here in the figure on the right. And other than PCBs, they also have a lot of applications in dielectric materials, and the mirrors that we have at home, they have a thin film of some reflecting material, then anti-reflection coatings, and they're used for filtering, not just for optics, but also for microwave and radio frequencies. So they have a lot of applications. One other very interesting application is quantum wells. So these can be used to trap electrons in a very narrow region, which can be tapped and can be used to study a lot of novel phenomena. So you guys must have heard about two-dimensional electron gas. So that comes from quantum wells, and quantum wells are essentially just layers of thin films of different materials, such that you have essentially well, well as in some kind of an energy well for electrons to fall into. So this here you have gas and gas on neither sides. You have gallium arsenide in the middle, and here the conduction band has comparatively lower energy. So electrons would obviously prefer to fall here. And so if you have a thin film of gallium arsenide between two aluminum gallium arsenide films, you can trap electrons here, which has had numerous applications, including transistors. Right. So methods of fabrication. Thin films, people have long realized they're very important. So they have also
Sonal,
come up. Yes.
so you are trapping electrons based on there's like a potential well or something.
Yes.
So
Yes. Yes.
okay, so okay.
So
Yeah,
here,
continue.
okay. Right. So there are physical methods and chemical methods for depositing thin films. So based on the thickness that you want and also the material you're depositing, there are a lot of methods you can choose from. If you want very high precision of the thickness you're going, say up to like single layers of atoms. Say you want only two layers of, want to deposit only two layers of atoms one on top of the other. There are methods like molecular beam epitaxy and atomic deposition layer. If you don't want very good control of the thickness, but you also want a thick coating. Say we deposit resists when we want to do electron beam lithography. So in that case, you do spin coating. So spin coating is just you deposit, if it is a liquid deposition, then you deposit a few drops of the material on top of the substrate you want to deposit it on, and then you spin your substrate. So the liquid spreads out evenly across your whole substrate. So I mean, these are very fascinating, and some of them surprisingly very simple ways of getting thin films.
Sonal, one thing.
Yeah.
How is the thickness important? I mean, like if you make it thinner, what would become better or what would become worse?
That depends on what you're making. It always depends on what you're making. So say I talked about electron beam lithography, and for that you need to deposit a resist on top. Now what the resist does is it will So electron beam lithography, in that case, you expose your resist to a beam of electrons, right? So depending on the thickness of the resist, the dosage of the electrons has to be changed, and like for how long you expose your resist to the electrons, that changes. Now, if the resist is very thick, you might have to wait 2 hours to make a structure on your uh, to make a structure. And if you have a thinner thickness of your resist, then you will need maybe like 15 minutes, 20 minutes. And not just that, so I will talk about superconducting nanowire single photon detectors, their thickness, so the thickness of the film for these devices, that could essentially be the difference between the device working or not working. If you make the thickness too thick, so too thick obviously will depend from device to device, but in that case, if it is more than say 20 nanometers for any SNSPD, then it will not work, because you also need good energy dissipation from your superconductor to your substrate. So depending on the device, there are different ways, and it could be the difference between make or break for your device.
Nice.
Yeah, so in my thesis especially, I worked on 3 thin film deposition methods: sputtering, electron beam evaporation, and thermal evaporation. So these I will discuss in a little bit of detail here. So first of all, sputtering. So sputtering involves the formation of a plasma. Plasma is ionized gas. So in this case, we have a high bias between the anode and the cathode. So you can see in the diagram shown on the right, there is a cathode on which we place the target material. This is just whatever material you want to deposit. And here on the anode, you have your substrate where you want to deposit your thin film. Now, because there is a high voltage difference, so any free electron initially that is close to your cathode, that is close to your anode, will be accelerated towards the cathode. When it reaches a high enough energy, it will collide with some argon atom here in the space itself. That ionizes that argon atom, leads to expulsion of another electron. Now, as electrons keep hitting and the number of electrons keep increasing, it will form a cascade, and you have essentially a plasma, because electrons, they keep hitting other argon atoms, electrons keep getting ejected, and also some electrons combine. So all of you know that plasma, you see it in tubelets, all of that is it has a visible glow. So that visible glow comes from recombination events. So initially we put the chamber in a vacuum. We want to remove water vapors and any other gases that could possibly react to the material that we would like to deposit, because we also want no contamination for thin films. This is very important for thin films. That is why in most of the methods that you see that I will be discussing here also, you need very good vacuum to get good concentration, and also so that your thin film is not contaminated. So sputtering is essentially mainly, there are also other types of sputtering, but there is DC sputtering and RF sputtering. So DC sputtering is used for conductors, and in this case you just have a DC bias across your cathode and anode. For semiconductors and insulators, now because you see here argon atoms, high energy argon ions, sorry, they go and strike your target. So if your target is not a conductor, it will continue to accumulate positive charge, right? Unless it can discharge off all of that into the rest of the circuit, here. So for semiconductors and insulators, because there is the voltage alternates, and like there is essentially no just one cathode or one anode, in the cycle where the target becomes the anode, all of that charge is discharged. And then in the next cycle, when the sign flips again for the electric field, you again have argon atoms hitting your target, and um, you have deposition. Also for RF sputtering, you need impedance matching. So some of you might know that when you want to transport RF voltage across a set of coaxial cables, the load at the end of your coaxial cable needs to be matched to the impedance of your coaxial cable. So that also needs to be accommodated for RF sputtering, which is why for RF sputtering you also need a much higher voltage than you need for DC sputtering for the same rates of deposition. Do you guys have any questions about this?
Oh, I think I missed the RF is radio frequency.
Yeah, radio frequency, yes.
Okay. So you're using radio waves to deposit your target on your anode or the substrate.
We're using radio frequency. So in DC sputtering, the voltage bias across the target and your substrate is DC. For semiconductor and insulator, it is the same setup, but in that case, you have an AC signal going in, AC signal in the RF radio frequency range. But essentially, the deposition is being done by plasma.
I mean, is there a specific reason why it has to be in the radio frequency range, or it can
in
be?
the radio frequency range? So first of all, radio frequency, it has been studied well enough, and you don't want the frequency to be so high that charge accumulates here on your target, and then that could lead to discharge here between the substrate and the target. You don't want that if like there isn't time enough for your target to discharge. So some frequencies, like very high frequencies, will essentially not serve that purpose. If the frequencies are very low, then at that point also at that point it is like kind of close to DC sputtering. Again, you will have charge accumulation on your target, and the plasma might also not sustain, because if argon atoms keep striking here and you have an increasing DC bias, again there will be a power discharge. So radio frequency kinds of fits in the balance, and also it is easier to match the impedance for radio frequency. It has been highly studied.
Thank you.
So, when you are depositing the material on the substrate, you see, above the anode, doesn't that cause a similar problem? I mean,
at the anode?
Yeah.
Right. So, yeah, this is something that I did not mention here, but so there is something called magnetron sputtering, and which is what is followed in most cases. So here, there is a magnet placed right below the cathode, which tries to confine electrons in this particular region, because you don't want a lot of electrons hitting your target, not just for the charge accumulation problem, but also because if high energy electrons hit your substrate, then it could lead to re-evaporation of the material you deposited on the substrate. You don't want that. So the problem of charge accumulation also is, and this will happen only for semiconductors and insulators only, because like for conductors, so anyway it will conduct off. But even in this case, electrons, because of presence of magnets here, right where the cathode is, electrons are confined to a region close to the target.
I think I get it.
Yeah. Did you understand that?
I think so, yeah. So substrate, because the electrons are confined to regions, the substrate is not really affected because of
the substrate is not affected so much, yes. The charge accumulation problem doesn't even arise there, because you try to keep the electrons away from the substrate.
Right, okay.
Can you give me 1 second? I am so sorry. Yes. Okay. Yeah, I am sorry about that. Yes, so sputtering. The other method is thermal evaporation. So this is also another physical deposition method, where you take a small amount of the material that you want to deposit, you heat it, and once it evaporates, you have a substrate right here on top waiting for all the electrons that are evaporated to go and strike here. So in this case, how do you provide enough heat to this one piece of material so that it evaporates? So there are these port kind of structures on which you can keep the pellet. And these ports are usually made of molybdenum or tungsten. And these are materials that have a high melting point, so that when you heat them up a lot, because the port also heats with the material, it doesn't melt, or some of it doesn't evaporate by itself and get mixed with the substance that you want to deposit. And you pass a very high electric current across your boat, and because of Joule's heating, it heats up, which also heats the material that you keep in the boat, and it evaporates. So in this process also, you need a very high vacuum of the order of 10 to the power minus 6 torr or lower. So that would roughly translate to like 10 to the power minus 9 atmosphere. And it's mostly metals that you deposit this way, because say semiconductors and all, they usually have much higher evaporation temperatures, temperature of evaporation. Right. So this was pretty simple. Do you have any questions for this? Right. Okay. So then the third method is electron beam evaporation. In this case, you have a target material placed, say, somewhere here in this diagram. And then you have a tungsten filament. Now, what that tungsten filament does is it is used as a source of electrons. You provide a very high bias across wires, across the tungsten wire, which reduces the work function. The work function is the amount of electric field then you then need to extract electrons from your tungsten wire out of the tungsten wire. So you guys might have read about Einstein's work on this thing, photoemission.
Photoelectric effect.
Photoelectric effect. I'm sorry. Yes, thank you. So yeah, so it is something like that, and your work function reduces because of a high bias across your tungsten wire. And then when you apply an electric field to extract the electrons and accelerate the electrons, after which a magnetic field directs the electrons that are emitted from your electron gun to exactly where your material is kept. And these electrons are high energy. So when they strike and dissipate their energy at the target material at a particular place, it heats up the material, which causes evaporation. So it is kind of like thermal evaporation, but in this case, there is very localized heating. You're not heating up everything. You're not even heating the container in which your material is kept. And the electron beam evaporation is usually faster. The rate of deposition is also higher. And even in this case, you need your chamber to be in a very high vacuum to not get contamination because of, say, water vapors present or oxygen present or nitride or anything that could react to the material that you want to deposit. Right. So yes, that was for fabrication. Now I will talk a little bit about superconductivity. So this is very basic. So for second, third year students. So superconductivity is the state in which your material has absolutely zero resistance to electric current and also perfect diamagnetism. Perfect diamagnetism is a magnetic field absolutely expelled from the bulk of the material. So if you do apply a magnetic field to a superconductor, none of it, if you measure magnetic field inside the bulk of the superconductor somehow, you will find zero magnetic field. So the temperature below which a conductor becomes a superconductor is called the transition temperature, and this phenomena of expulsion of magnetic field from a superconductor is known as Meissner effect. So this is one really important and kind of cool way of understanding what the difference is between a perfect conductor, which is a conductor which has zero resistance, but only zero resistance, and a superconductor. So you have a perfect conductor here, which is in the presence of a magnetic field, and the magnetic field is going from the bulk of the material also. Now, when you cool it down, you will still have magnetic field going through your material. Now, when you remove the magnetic field, because so you guys must have heard about rate of the magnetic field. Any material does not want magnetic field inside it to not change. So which is why when you remove the magnetic field at a later stage, after cooling it down to the perfect conductor to 0 Kelvin, there will be self-induced currents which will produce the same magnetic field as there was before you remove the magnetic field. In a superconductor, however, so this is a normal conductor in the presence of a magnetic field which is going through its bulk also. But when you cool it down to below the transition temperature, it will expel any and all magnetic field that is going through the bulk of the material. And also, when you remove that magnetic field, there will be no self-induced currents in your superconductor. So one interesting thing is how does a superconductor cancel any magnetic field inside it once it becomes superconducting. So there are shielding currents that arise only in a particular thickness, which is called the penetration depth of a superconductor, which cancel all the magnetic fields inside. And superconductors are classified in two types, type 1 superconductor and type 2 superconductor. So type 2 superconductors have the property of partial expulsion of a magnetic field. So above a certain critical magnetic field, they will allow, say, a small amount of the magnetic field to go through them, but they still maintain superconductivity in most of their bulk. So I mentioned that here because the two superconductors that I worked with, titanium palladium alloy and molybdenum germanium alloy, they're both type 2 superconductors. So I'll start with a little literature review. So based on the work people have done on titanium and palladium, they have shown superconductivity around 3.7 Kelvin, and the concentrations especially are really important. You see the concentrations here are changing just a little bit, and that's causing a significant change in the transition temperature. Right, for molybdenum germanium alloy also, again type 2 superconductor, and in this case,
Sonal,
yeah.
an off-topic question. So, how rare are these? Like, how expensive are these?
Okay, so again, palladium we all know is so palladium I was told is 3 times more expensive than gold, because if we're talking about, I told earlier that we need very good, we don't want any contamination, we don't want the slightest bit of oxygen in
Right.
the chamber. So you also want that the pellet that you're working with, the sample material that you're working with, is very pure. Now anything, and that's true for any material, honestly, anything that you're working with, it has to be very pure, and the more pure your material is that you buy, the more expensive it is going to be. So the palladium I worked with was 99.998% pure, and apparently 3 times more expensive than gold. And you need significant amounts of these also. So yeah, it's pretty expensive. Yeah, so for molybdenum germanium, you need germanium's concentration in the range of 10 to 30% if you want superconductivity. And if the concentration is above that, then then you won't find superconductivity. So that is again something that is very important. The exact ratio of the concentration is something that you will have to try. You need to know your machine very well. You need to spend a lot of time. You need to make multiple samples to finally get the right concentration. And even when you get that right, sometimes things don't work out, or in the next, something that there might be a little bit of oxygen, a little bit more oxygen than you would want, and that could deteriorate your transition temperature. So essentially, experiments are hard. Oh, so another thing. So depending on the thickness of the film, the transition temperature can change. So the transition temperature for the bulk is say 5 Kelvin, but if you have a film that with thickness of say 10 nanometers or 15 nanometers, its transition temperature could be only say 3 Kelvin. Yeah, so that is again another thing you need to look out for thin films. So how I fabricated them. So for molybdenum and germanium, I used DC and RF sputtering that I told earlier, and they were co-deposited. I deposited them at the same time. And again, so like the substrate I used was silicon nitride. For titanium and palladium, I used electron beam evaporation to deposit titanium, and palladium, I used thermal evaporation. And in this case, I couldn't co-deposit them. I couldn't deposit them at the same time. So I deposited alternate layers of titanium and palladium. So this was again one of the first times like we were trying to make an alloy out of alternate layers of two different materials. And to ensure that it did become an alloy, we did two things. First, when we deposited, we kept the substrate. The substrate is the material on which we deposited the thin films at a high temperature of 250 degrees Celsius. And also, after the films were deposited, we annealed them. So annealing is heating them in the absence of oxygen, uh, so that the layers intermix and we get an alloy. Because an alloy will have a transition temperature of 3.5 Kelvin. If say you just have titanium becomes superconducting at like below zero point 0.8 Kelvin. So you don't want just titanium, which is why intermixing and formation of alloy is really important. Okay, so a little bit about the lab. These are pictures, all of them are from the ultra low temperature lab at ISO Mohali. This is the sputtering setup. This is the impedance matching for RF system. This is the RF power supply. This is the DC power supply. Turbo control. So turbo is a turbomolecular pump, which allows you to achieve very high vacuums of the order of 10 to the power -6 torr or -7 torr. And this here is plasma. So yay, sometimes lab, sometimes it's pretty. Um, yeah, and this is the electron gun evaporator. This here is the turbo again. You need a lot of things to make it work. And then finally, this is the thermal annealing setup. So, okay, one disclaimer here. Experiments take a lot of time, a lot of time. You could be working in lab all day and you need to do it and then redo it. And even then, when you know everything, you might not be able to repeat an experiment because a lot of things are out of your control. So you should always be patient with experiments. Also, it takes a lot of physical work and there are also risks. So in the electron gun evaporation, this power supply provides a voltage of 10 kilovolts. So if when you open your chamber after doing an electron beam evaporation, and you always need to ground it. You need to ground for any charge accumulations, because if you don't, you might get a shock which could be fatal. So there are always a lot of risks involved with experimental work. Not to scare you, but it's important to know these things. And yes, but experiments are super fun. Please don't tell me at the end of like 2 years or 3 years we chose theory just because experiments are risky and this one particular senior told us it's not nice. They're fun, trust me. Okay, so right, once you have the films deposited, what you need now is to ensure that you have the right concentration of the material that you deposited. So these are uh, figures of the concentrations that I got. Now, how do you figure out what is the concentration? So for that, we do something called energy dispersive X-ray spectroscopy. And this is the picture of a scanning electron microscope, which helps us do energy dispersive X-ray spectroscopy. Now, this is done in an SEM, and it is used to determine the composition of the fabricated thin films. Now, every material has a unique electromagnetic emission spectrum. So, what?
There's
Yeah.
a question in the chat. So, SD, whoever it is, you can say.
Wait, I'll read it.
Or read it, yeah.
Okay. Oh yeah, sure. So if you want, 1 second. Okay. Yeah. So I'm sorry. So so I mean, since you're talking about cost, yes, a lot of material is wasted. So even when you're evaporating everywhere. So I guess energy efficient would be, first of all, having a smaller chamber of deposition. So that has been achieved for sputtering. So for gold sputtering and palladium sputtering, you get, for gold sputtering especially, even in ultra low temperature lab, you have a sputtering chamber that is like this bigger size. So that leads to lesser wasting. Also because there is selective evaporation for selective evaporation in the same electron beam evaporation. In that case, you tend to use lesser of your material. I think thermal evaporation is the one that wastes your material a lot, especially for expensive materials. But okay, that is the question of wasting. Now, if you think, okay, so because electron beam evaporation is more effective, it gives you a high rate of evaporation, we should use palladium in an electron beam evaporator. That we can't do, because palladium will need a significant amount of the target material initially. Like, you will need, say, a bigger chunk of palladium to keep in your crucible where you evaporate the palladium. That is very expensive. If you just want to do thermal evaporation, you need a tiny pellet, like, I don't know, an inch of it to do the thermal evaporation. So that does waste more of the palladium, but you can get, you need lesser investment at the moment to get it done. So I guess that's about it. Okay, so energy dispersive X-ray spectroscopy. So in this case, a scanning electron microscope has it has an electron source that hits with really high energy whatever material you want to study. So in this case, these high energy electrons knock out the orbital electrons of whatever materials are inside. And when these electrons that have been knocked out, they create holes. These holes are filled in by electrons from higher energy levels that come down. And when they come down, say an electron in your L shell has been knocked out, it is filled out by K shell or M shell, and it's filled out by M shell or N shell. And because the electron is losing some energy, it will release a photon. That photon is detected by a photon detector, which can measure the energy of the photon and also the number of photons that have been detected for the same energy. So at the end of the day, you bombard a lot of electrons, you collect a lot of photons emitted from your sample, and because every element also has a unique spectrum. So we know the exact energy of a photon that will come when an L shell electron is knocked out from, say, molybdenum, and it is replenished by the M shell electron in molybdenum itself. So all of these things are noted, and there is a code written out to determine that if, like, this is the set of photons, energy set of photons that you get, then it will be this particular material. And similarly, all other elements. And based on the number of photons you get for each energy, you can also figure out the concentration of the material that is present in your sample. So that's how you get this diagram here. Oh, sorry. That's how you get this diagram here. See, you observe a lot of photons here. So this is for silicon, this big one. This is for oxide, because there is a small layer of silicon oxide on your silicon substrate. Then you have titanium and palladium. So this higher, another peak of titanium is because of a higher energy photon. Say if your L shell electron is knocked out, it is filled out by O shell or N shell instead of the M shell. Right. So was that clear? Like, please ask questions. If it is not clear, I will happily explain it again. Okay. I
So
really
that
hope.
you had that peaks, right?
Yeah.
You go back to that.
Yeah.
So that basically comes from how many electrons how many photons have been produced at that energy.
Yeah. At this energy, how many photons are detected? Correct. So I mean, say here, I detect a particular number of electrons for titanium. I detect, so it's hard to see here because these other peaks are quite big. But if I zoom in, then for palladium the peak is much smaller, which means the concentration of palladium is also much smaller. And you can see here, like, palladium was around 20% of the sample, titanium was around 80% of the sample. So yes, the peak. The height of the peak basically is directly proportional to their concentration in the sample that you want to examine. So yes, I got the results here, and so you need to fix out a lot of parameters. So at one particular parameter of DC current for my molybdenum target, I got roughly the concentration of 75:25, which I expected should give me a transition temperature for MOGE of around 5 Kelvin. and I kept the film thickness at 100 nanometers. For titanium and palladium also, similarly, I got the concentrations that I wanted. And one way to figure out if, because for titanium and palladium, I deposited alternate layers. So to figure out if there has indeed been mixing and stuff, you take your ADX samples from multiple places on your sample. So for ADX, you can't do an ADX if you have a 1 centimeter by 1 centimeter sample. You can't do an ADX for the whole thing because you need to be very specific in your region. So if you pick different regions from your sample, then you can figure out if there is uniformity of the concentration. If there is uniformity, that means there is also significant diffusion on your chip, which is good, which means you will have an alloy instead of just alternate layers of titanium and palladium. Right. So
And how long does it take to generate one whole alloy that you are saying?
Okay, so sputtering, yes, like I said, it's a lengthy process. So for any deposition that you do, you need to reach the place at least 6 hours before. If you need a good vacuum, you need to start your turbo pump. It takes 5 to 6 hours to reach a high vacuum. High vacuum is 10 to the power minus 6 torr or below. So that when you start depositing for sputtering, you can deposit for say like half an hour or 40 minutes. And for electron beam evaporation, and since I was doing alternate depositions, it took me about 4 hours of continuous deposition because there is waiting time between doing the electron beam evaporation and the thermal evaporation. You need to wait for the system to cool down before using it again and all that. So roughly 4 hours to deposit 4 layers of titanium and palladium each. And then you need to like switch off your system, wait for the turbo to, it takes another hour to get your chips out of the chamber, waiting for the turbo to come down to 0, and then like all these things. So time consuming, yes.
And then you do that amalgamation, right?
Oh yeah, and
process.
Then the annealing process, yes.
Annealing, yeah.
Yeah, then you do annealing. So for that you have to be very precise. You need to say you do the annealing for 10 minutes, but to reach the temperature at which you want to anneal your sample, you set your PDC, PIC. The PIC is what controls your temperature increase. You set it ki half an hour mein the setup, the annealer should reach 450 degrees Celsius, and then it will anneal at 450 degrees Celsius for say 10 minutes, and then it will cool down. The cooling down again takes some 2-3 hours. So yes, that is also time consuming.
Sonell, how is the thickness measured of the film?
Oh, the thickness measuring of the film. So there are 2 ways of doing that. The more efficient way is that you have a quartz crystal microbalance. I have not mentioned it here, but what it essentially does is quartz crystal, has a particular frequency of vibration, around 13.3 or 4 megahertz. So you have a quartz crystal microbalance. Now you keep the quartz crystal in the same chamber as you have your substrate. Now, when there is deposition on the substrate, there is also deposition on your microbalance, the quartz microbalance. And as it keeps material keeps depositing on it, its weight will keep changing, which means the resonant frequency of vibration of your crystal also keeps changing. And there is a very efficient code to figure out exactly how much thickness has been deposited.
So the precision, you can measure it up to like a nanometer. That's
no, you can actually measure it up to an angstrom, honestly.
Oh, okay.
Like 1 or 2 angstrom. So it's very efficient. It's very precise, the quartz crystal microbalance, especially when you have a new QCM. As it gets old, it reaches age, then it becomes less precise. But yes, you can measure up to 1 or 2 angstrom. That's pretty good precision.
And all of these thickness, concentration, everything is then used to determine the transition temperature, I guess. I mean,
Yes,
get an estimate of. Okay.
So yes, you always have some estimate, but Yeah, you always have some estimate. If this is how much the thickness that I'm depositing, I'm expecting this much of a transition temperature. But in a lot of cases, it'll be different, because say the argon gas that I'm using, if it is not as pure as what was used in some other paper in some other lab, my transition temperature could be lower. Or if it is more pure than the argon that some other lab has used, I could get a better transition temperature. Or if
Yeah.
my vacuum pump is much better than somewhere else, I could get better results. So it's not just thickness, a lot of other things can play a much more significant role in this. So you need to look out for a lot of things. Yes.
Yeah. Okay.
Yeah, and oh yeah, and the other way of measuring thickness, if you can't fit a post-crystal microbalance in your chamber while depositing, is to once you deposit the film, say I deposited the film for 10 minutes, then I go to the scanning electron microscope. In the scanning electron microscope, you can image very well using electrons. So there
Okay.
I can measure the thickness of the film. It's essentially a microscope. You zoom in a lot and then you find out the precise thickness of your film. So if I deposited for 10 minutes, I got a thickness of 50 nanometers. So roughly, if I deposit for 20 minutes, I should roughly get 100 nanometers.
Okay.
Yes, that is the hard way of doing it.
All right. Thanks. Thanks for the answer.
Right. So now that we're done with fabrication, how do we measure properties in any system? So electrical measurements, we've all studied the two-probe measurement, where like you have one device and you connect probes on two sides, and you use that to supply the current and also to measure the voltage across the sample. Now, in that case, there are two things to look out for. One is contact resistance. Contact resistance is the resistance. So this is my probe. The contact between the probe and my sample will also have some resistance, which will add to the resistance of my sample. And the second is the resistance in this lead wire, the wire that connects to the ammeter and goes through it. So a better way of finding resistance, especially in samples that have very low resistance of themselves. Say if my sample resistance is 1 ohm and my contact resistance is 100 ohms, then the two probe method will be absolutely useless. So in that case, people have come up with a four probe measurement. Now, what a four probe measurement does is you have one set of probes connecting to the ammeter, which will measure the current across your sample, and you have a constant power supply here. The second set of probes, and that is placed inside of these current measurement, the sense probes. So these connect to a voltmeter, which is in parallel to your sample. Now, in this case, the voltmeter has a very high resistance. So any current that comes through your power supply will mostly pass through your sample only, because the voltmeter has a very high resistance. If they're in parallel, most of the current will pass through here. And now most of the current is passing through um, only your sample, and also any resistance that comes from this wire or these contacts here will not be measured, because you're only measuring the voltage between the point 2 and 3 here. So like resistance that comes in from this region or this region will not be counted. So you can very precisely measure without contact or lead wire resistance added to your sample resistance, uh, the precise resistance of your sample basically. So yes, you get high accuracy, and especially when we talk about superconductors, where we want to see if there is indeed zero resistance or not. So for those cases, four-probe measurement is the only way to find the resistance versus temperature characteristic of any sample, which is how people find the transition temperature of superconductors. They make an RT curve, and the temperature at which resistance drops to zero is the transition temperature. So that is the four-probe method of doing it. What I did in my experiment, in my thesis, was finding a one-probe measurement one-probe transition temperature measurement. Okay. Okay, so in the one probe transition measurement, I only have one probe going in, touching my sample. The other end is connected to the ground. So DUT is the device under test. This is my thin film. I have only one single wire going into my device. The other I have connected to the ground. I have a lock-in amplifier which gives me an AC signal input connected to bidirectional coupler. It gives the input. Then here I talked about Meissner effect. So Meissner effect is expulsion of magnetic field. Now, since all of you know that AC field is alternating electric field, like the direction of electric field keeps changing, which means there will also be a magnetic field arising from any AC signal, right? So because an AC signal will produce a magnetic field, if I send in an AC signal across a conductor, all of it will go and be grounded. Once my device becomes superconducting, the AC signal will be reflected from our thin film. Right. So I had an AC output. I sent in a signal of around 2 megahertz. That goes in from here, goes to my device, and this is a bidirectional coupler. Now, since I said the AC signal will be reflected once the device under test becomes superconducting, what this coupler does is it has 4 ports. Now, this port here, if I send in any signal from this port here, it will couple to this port and to this port, but port 4 here will be isolated. Nothing will go in here. So when I want to see if whatever signal I have come here and I want to analyze it, I can connect it to this port and check whatever signal is coming back. Now, a lock-in amplifier, especially for first and second year students who don't know, is you can select a very particular frequency that you want to measure, because the signal will be very small. The reflected signal will be very small, because in a bidirectional coupler, most of the signal will go here into port 2, and with almost a 10 dB power reduction, some of it will come to the signal analyzer. If you know the exact frequency, which we know because we're giving in the AC input to our device, if we know that exact frequency, then we can check for that frequency and see how much of that frequency signal is coming, the amplitude of the signal that is coming in. So yeah, I guess that's.
So I have a doubt here with the bidirectional coupler.
Yes.
So the reflected current after say your DUT becomes superconducting and the signal is reflected, how do I know all of it goes to the signal analyzer?
How do you know all of it goes to the signal analyzer?
Yeah.
Oh no, it doesn't. Okay. So the point of the bidirectional coupler here is, if I send in a signal from here, it will only go to port 3. Port 4 is isolated. So the point here is the signal that I send in from here, the AC output, that shouldn't couple to port 3 where I'm analyzing the signal. Because that is input signal, that is not the reflected signal.
Right.
The reflected signal that comes out, some of it goes to this port 2 here, some of it goes to port 3.
Okay, some of it goes. Okay.
Yeah, some of it. There is a roughly 10 dB power reduction, but some of it goes here. But the point is, you shouldn't have any of this input signal that we're giving going into port 3. That defeats the purpose of analyzing the reflected signal.
Right.
Yeah.
Okay, thanks.
Yeah, so I guess I use too many words here, but the point is, you send an AC signal and you want to see if it is being reflected back. It will reflect back when your thin film becomes superconducting, and you want to see when it will become superconducting. That is the gist of it. Right. So I tried 2 methods for the Oneprobe Tc measurement. One was using. I'm sorry.
Hello, there is a question. How does this bidirectional coupler work? So, like,
how does it work?
I'm interested in the mechanism that. You understand my question?
I do actually. So honestly, I do not know the full mechanism of the bidirectional coupler.
It's an electronic device, right?
Yeah, it's an electronic device. It doesn't need. It's not an active device. It's a passive device. Like, you don't need to give it some kind of electric current for it to work in this way. I think it has something to do with the port connection only, I think. Honestly, I'm not sure. I will look it up and get back to you.
Sure.
No, that's a good question, honestly. I will look it up and get back to you.
Maybe diode will be working there, like, it's like differentiating the direction of the current, right? So,
Yeah.
Maybe, I don't know actually. I just
Yeah,
I
you're
was
right.
just
You're
maybe.
right. That could be possible. There is indeed a circuit diagram also for how the bidirectional coupler works. And right after the talk, I will look it up and I will get back to you. And I'll also post it on the Discord server, the answer that I get, so that everybody can look at it. I'm so sorry about this, though.
No, it's fine. It's good.
Okay, so yeah, so the first method, I deposited my molybdenum and germanium alloy directly on a quartz crystal, which I put on a PCB that I put inside the dilution fridge. So this is essentially the device under test right here. And I have these two clips coming in that are touching my thin film directly. And I send in, this is the input probe. This is where the AC signal comes in and also is reflected. The other end is grounded. Okay, so I deposited the molybdenum and germanium alloy in the particular ratio that I wanted, and I put a 50 ohm resistor here that is going to the ground. Now, I mentioned earlier that if you send in an RF signal, then you also need impedance matching. Impedance matching in this case, because most coaxial cables have an impedance of themselves of around 50 ohms. So if I if I add a 50 ohm resistor here that goes to the ground, then most of my signal, like there will be no signal loss, and most of my signal will come in here through the sample. And I used a paste called G varnish, which is not very important, but it has good thermal conductivity. Also, the PCB that I used, it is made of a material which has very good thermal conductivity, because the sample that I made is not in direct contact with the dilution fridge. It is this PCB. So this PCB and also the paste that I used to paste my thin film on the PCB should transfer any heat on my sample out to the dilution fridge, so that my thin film reaches a very low enough temperature. And this is a picture. I mean, this is the quartz crystal, this is the PCB. So this is the graph that we got. We took a temperature versus the voltage graph. So we're decreasing the temperature here. This is 1 Kelvin. Starting 1 Kelvin, the reflected signal saw a pretty significant increase, which means starting 1 Kelvin, the sample, the thin film, became superconducting. And we took this measurement at a frequency of 2.35 megahertz. So honestly, I really want you guys to understand how this is working.
Sonal, so there is, in 2 minutes, there's a break. So if you want to wait here, or is there another slide? There are 2 minutes for the break.
No, this is it for my first method. Then I have the second method. And
okay, then
yeah,
I guess we can take a break right now.
Yeah. Okay.
Right?
Let's take a 5-minute break right now. We'll meet
Yeah.
at 5:05.
Yeah, sure.
Okay.
If there are any questions, then I guess.
Oh yeah. Okay, so to reiterate what's happening, you send in an AC signal to hopefully what is your superconductor, and because it is a superconductor, it will reflect back your AC signal. Now we catch that reflected part, send it to a signal analyzer, and we keep analyzing what the amplitude of the reflected signal at the particular frequency is, the particular frequency of your input signal. Right, and when your reflected signal starts increasing, that is an indication of transition to superconductivity. So yay, you do have a superconductor. Yes, so the second method that I used was using a microstrip. So in this case, there was no direct contact, no direct electrical contact of the thin film with the input probe. Like in this case, I relied on magnetic coupling between the thin film and the microstrip right here. So microstrip is the structure. This is a PCB. This is the input probe. I send in my AC signal here. So when my thin film becomes superconducting, I expect, because there is perfect diamagnetism here, and some of it will affect the AC signal going in from the microstrip. And I expect the signal, the reflected signal, to increase. Like some of the signal will always reflect, like say some of it will pass through to the ground, but there should be some increase in the reflected signal when I have a superconducting thin film placed very close in contact to my microstrip. So,
Sonal,
yeah,
the black material there is the thin film, right?
here,
Yeah. What is, yeah, is that it?
this.
Yeah.
Yes, can you see my cursor actually?
Yeah, yeah.
Okay. Yeah, so this is the thin film. I pasted it upside down. This is the substrate. The thin film I
Okay.
deposited on the other side because I want that thin film to be as close to the copper microstrip as possible.
Right. And
Yeah.
the probe is there on the
This
other
is the
side,
probe.
right?
This
Oh,
is the
that's the
probe.
probe.
Yeah,
Okay.
and this is a surface mount resistor, 50 ohms, which I've grounded.
Right. Okay.
Yeah, and yeah, so here I checked for TIPD, and the results were not very exciting. We got a very random graph for reflectivity and essentially no clear signature that there was a transition to superconductivity. This also we did at the same input frequency signal. This could also be because magnetic coupling is a much weaker
There's a
phenomenon
question.
to rely on. Yeah.
So someone is asking, Ajit, what is
So
ULTP?
what is ULTP on the PCB? ULTP is ultra low temperature lab headed by Dr. Anand Venkatesan. So yes, we worked in that lab. Like yes, this PCB is a product of ULTP lab. Yeah. So yes, we did not observe a clear signature of superconductivity for the titanium palladium thin film. And also magnetic coupling is a much weaker phenomenon to depend on. The reason I decided to go with the microstrip method and not have direct contact with the thin film was because we were putting the sample in a dilution refrigerator. Now, to make contacts on a thin film itself. So earlier we used a quartz crystal, and there are clips that you can connect on the quartz crystal. Now, if you have a sample that has been made on a silicon chip, you can't use clips like that. You will have to use surface contacts. And these contacts are very hard to make. They're made of very thin gold wires and indium solder, and you need to press it on, and they also come apart very easily. So if you keep your sample in a dilution fridge, you cool it down for 2 days, and then you finally realize that your contact has come off, then you need to reheat the fridge for another 7 days. Take your sample out, put the top contact again, and then put it back in and pray to God that your top contact doesn't come off. Which is why I decided to see if magnetic coupling could help me solve that particular problem. And
Sonal, there's another question by Ajit.
yeah.
You are talking about the reflected signal. Is not it here? You should be looking at the transmitted signal. So are you basically looking at? Yeah.
Oh, okay. So, okay, here's the thing. This is Oneprobe Tc measurement. If I look at the transmitted signal, then I will need 2 probes. Now, in a dilution fridge, I will tell you why I am talking about 1 probe. Because you can't send in a lot of wires into your dilution fridge. The dilution fridge goes to temperatures as low as 10 millikelvin. Now, if I have 20 wires going into my dilution fridge, and copper in itself is a very good thermal conductor. So if I have all those wires going into my dilution fridge, it will take me much longer to cool down my system down to the temperatures that I am hoping to seek. So there are very limited number of probes. Now, if you want to measure, and because like I mentioned, it will take you a whole cycle of 8 to 9 days to measure one batch of samples. The more number of samples that I can measure at one time, say I keep 3 samples or 4 samples into my dilution fridge, that's better than measuring one at a time. If I have only 4 probes, that means I can measure only one sample at a time. But if this one probe measurement can work, then I can keep in 4 samples and measure Tc for all of those samples. Does that answer your question? So like basically you can do that. Obviously you can do that, but that needs one more probe, one less sample. Right. Is it? Yes. So this is the device, the AIM device, superconducting nanowire single-photon detector. So I will actually get to the picture first of the meander geometry. So this is what the meander geometry looks like. It's basically a reverse meander in planes, stuff like that. So yes, let's start from the beginning. These are single photon detectors. You can actually detect like just one photon from any single photon detectors. There are multiple single photon detectors, one of which is SNSPD. And these detectors can be used in quantum computing for quantum key distribution, for LiDAR experiments, which is kind of like radar, but it uses light and especially entangled photons to detect long distance objects. Then also space Earth communications and things like that. SNSPDs can be used to detect a wide range of radiation. So the wavelength of the photon can range from 200 nanometers to 2 micrometers, which is in itself a pretty wide range of photons to detect. Most single photon detectors have a range of, say, if they start with nanometers, they can only detect up to, say, a few thousand nanometers. And then there are other single photon detectors that measure for higher wavelength photons. So SNSPD's one advantage is that they have a pretty high range. Now also you can, in order to get this high range, there are a few parameters that you can vary, like the width of the nanowires of that meander structure that I showed you. You can vary its width, the bias current, which is the current that you pass through your superconductor in order to detect a photon, and also the choice of your superconductor that you use to make your SNSPD to detect a particular wavelength. Also SNSPDs. So some other single photon detectors are SPADs, avalanche photodiodes basically. Then single photon avalanche photodiodes, kinetic inductance detectors, transition net sensors. But the SNSPDs have shown much faster recovery times. So every single photon detector needs a recovery time. If it detects a photon, then it needs to recover. How we detect a photon is basically for superconductor based photons. It transitions from superconductivity to a normal metal, and it obtains some resistance, which creates a pulse. And after that, it needs to cool down again, go back to being a superconductor before it detects the next photon. So in that case, we need very fast recovery times, and also a good detection efficiency. We don't want it to miss out on photons, or we also don't want it to have to detect a lot of background photons that come in from other energy ranges. So because it is so maneuverable, it has shown better efficiency and also faster recovery time. So the meander geometry that I showed you, they are usually made in meander geometry, and that you can make using electron beam lithography. The device is kept at a DC bias. So superconductors have a critical current density. If you pass a current across a superconductor above a certain value, it will become a conductor. So what we do is we have a current running through running through our SNSPD just below the DC bias. So if there is if IC is the critical current, we have like 97% of IC we pass through a superconducting nanowire single photon detector. Now I will tell you how it works. So first we have our SNSPD, which has the bias current, 97% of the critical current running across it. Now, when a photon falls on the SNSPD, the nanowire part of it, it gets absorbed here. That energy dissipates into the material, and this particular region becomes locally heated. Now, because this region is heated, that means it has a certain resistivity. So all of the current that you send here, it will be redirected. It starts flowing around this normal conductor region. Now, because we're so close to the critical current already, in these regions where it starts flowing, the critical current density exceeds the critical current density of the maximum that the superconductor can handle. So because critical current density has been exceeded, this whole region, the whole width of the nanowire, the whole width of the nanowire will become, will cease from being a superconductor. And you have a resistance across the whole width, which means current flow will stop. So there is a parallel circuit to our single SNSPD, which has a resistance less than what we expect here. So usually even for thickness, even for a nanowire of width, say like 100, 200 nanometers, we will expect for MOGE, say it will be around 200 ohms. Here, the resistance, if the whole width here becomes normal, ceases from being superconducting. So in parallel to our SNSPD, we keep a 50 ohm resistor where all of the current will be redirected. Now the resistive region here increases because of Joule's heating, and the current starts flowing through that shunt circuit, which has a smaller resistance than our SNSPD. And because the current has been redirected, now there is no current passing through our SNSPD, which allows it to time to cool down. No continuous Joule's heating, so it will cool down, and then the next cycle starts. Then again, the current which has gone through the shunt circuit will start flowing from our SNSPD once it becomes superconducting again, and it can absorb the next photon. So was that clear?
Yes.
Sonal,
I have one question. Maybe Samir.
you go.
Okay, thanks. So, how long does this whole cycle take?
Okay. Yeah.
And
So,
also, how long does step 6 to step 1, that is the dead time for which you wait SNPD to cool down? How long is that?
So tau 1, it's divided in two parts, tau 1 and tau 2. Tau 1 takes about, I think, a few picoseconds. This doesn't take very long, like photon absorbed and then quickly spreading of the heat. Tau 2 is what we call the dead time, and that could range depending on how good your SNSPD is, how thick your thin film is. Like this is also where the thickness of your SNSPD matters, because how the energy dissipates is the electrons are basically heated. What happens here when this hotspot is created is in this region, the Cooper pair will break down. Okay, and these electrons now will have a very high energy and they're going about everywhere, heating everything up. These electrons will interact with phonons of the lattice of the superconductor and also the substrate. Ultimately, you want all of the heat to transfer to the substrate and down to the dilution fridge, right? So if the film is very thick, it could take longer. And if you have an ideal SNSPD, it shouldn't take more than, I would say, 20, 30, 40 picoseconds for the dead time for very good SNSPDs. If your film thickness is thicker, it could take up to a nanosecond, which means you'll miss out on a lot of photons. So in the dead time, this SNSPD cannot detect a photon.
So I have a doubt. Here, I missed the point where this becomes a single photon detector. As in, why does it detect only a single photon and not two photons? For example, we know that its photons are bosons. So how does it differentiate between two photons being absorbed and not? Because all I can see is detection here, not really a single photon.
Yeah. So if say two photons have been absorbed here at the same time, there is no way of you knowing if a photon has been absorbed at some other place on the SNSPD. That is why single photon detection, when you're expecting anti-bunched photons. So anti-bunched photons are when you have one photon coming in at one time. You don't have 2-3 photons coming in simultaneously.
Right, okay.
Yeah. Okay. So and that is also how, so this is a little side note, but that is also how you check if your source has anti-bunched photons, is giving anti-bunched photons as in one photon at a time, or just multiple photons at one time. You place a beam splitter and you have two single photon detectors on the two outputs. And if both of them detect photons, you also have a timer on both of them. So you keep timing at what time both of them keep detecting photons. And if you see if there is a lot of overlap between the times that both of them detect photons, then you know that a lot of them are coming in simultaneously. But if both the single photon detectors detect photons at different times, then that means you're getting anti-bunched photons from your source, the photon source. Right. So
basically coincidence count, right?
Yeah, coincidence count, exactly. G2 correlation. Yeah. So this experiment is called Hanbury-Brown twist experiment. You must know about that. Yeah, so HPT experiment that is used to precisely to do G2 correlation. Coincidence count. Right. Experimental parameters, not important, but one thing I would like to mention is that the thin films that we make, we want them to be amorphous and not crystalline. Now, why we want that is because we want the heat to be dissipated very quickly. Now, when you have these high energy electrons that arise when the Cooper pair breaks, if the coherence length is too large, it will take them longer for them to hit other phonons and like basically the crystal and transfer their heat down to the substrate. But for amorphous thin films, since the coherence length is very small, the electron will much sooner hit some part of the lattice and transfer its energy, which is why they're much easier to cool down, much faster to cool down. Also, crystalline thin films will have non-uniformities for especially because they're thin films. So you will have sectionalization. You will have what are called these crystal boundaries. You might have multiple crystal boundaries for crystalline thin films, which again suppresses superconducting properties for very thin films. And yeah, the film thickness should range between 5 nanometers to 10 nanometers if you want to detect a photon in the range of 1500 nanometers. Now 1550 nanometers, as some of you might know, is the telecommunication wavelength, which is used in optic fibers, because that is the photon that is least absorbed when being transmitted over a long distance, like least diffusion of the power. Right, and this is what the readout circuit for a single SNSPD looks like. Here, yeah, so here you have a DC bias. You have a bias current flowing in that goes in from your SNSPD. That is 97%. Here you have a bias T. What a bias T does is, through this capacitor output, it will only allow RF signals to go out. Here in the inductance part, it will only allow DC signals to go out. So you have a bias current in your SNSPD here. As soon as it detects a photon, there will be a pulse across. So in this diagram here on the right, this is the shunt circuit. The resistor that is the resistor that is in parallel to your SNSPD. This is the SNSPD, this is your resistor in parallel. And across this resistor, we measure if there is a pulse of electric current. So as soon as there is a tiny signal across it, a tiny duration across which current flows through a shunt resistor, that means a photon has been detected in our SNSPD. Was that clear? Do you want me to repeat that? Okay, I hope you guys got that. So yes, as soon as current flows across our shunt resistor, that means a photon has been detected in the SNSPD. So we measure this pulse, and this pulse goes into our bias T, and the RF signal goes here into the counter oscilloscope or the photon counter. After being amplified, the signal is amplified, and the DC part of it goes back, completes the circuit, and the DC bias continues across our shunt circuit and our SNSPD. So that's how you measure photons as they come in. You look for these pulses across the shunt resistor and see exactly when photons have been detected, and one photon now, then 10 nanoseconds later you detect another photon and things like that. So this is the readout circuit, how you use the SNSPD. So yeah, that's it. Thank you. Do you guys have questions? Did you guys understand anything?
Yeah, I mean, yes, it was very informative.
Hey,
And
Sonal,
Yeah.
yeah. So this is a general question. Is this is the first step to make squids? Like, do we need all? You know, squids?
Yeah, I know squids. Yes.
Yeah.
Squids
So
are just two Josephson junctions in
yeah,
parallel.
yeah. So do we always need these kind of films for that also?
Oh yes, definitely. Like for
Okay.
squids, you
So
need to make the Josephson
okay. So
junction.
this is first step to make Josephson.
Exactly. Thin film fabrication is the first step to making Josephson junctions.
Okay.
Yes. And then you have device fabrication everything. So that obviously again comes into it. So E-beam lithography, again, you need to make the squid structure after thin film deposition.
Okay.
Yeah.
Sonal, what is that bias T?
Oh, the bias T, yes. So this is essentially very simple. It's just a normal wire going in here. One output is connected to an inductor. The other is connected to a capacitor. The capacitor will only allow RF, AC signals to pass across it.
Oh, okay.
DC will be blocked here. And AC, similarly, AC will be blocked here across the inductor. Only DC signals will pass here. So this is basically to detect the RF signal. So if there is an RF signal, which is essentially the pulse that you see across your shunt resistor, like that's a pulse, right? So that's an AC output.
Right.
Yeah, so that you want, if there is any pulse, it will go across the bias T through the amplifier into the photon counter. And the other end completes the circuit of bias, this bias circuit.
Okay, thanks. Yeah.
And again, as we have discussed earlier, you need your SNSPD to be a superconductor in the first place. So this device needs to be kept at a very low temperature inside a cryostat, and also with an optical window on top where you can illuminate it with with whatever photon source you have. So that is one disadvantage. You can't use it at room temperature.
Any more questions? So I guess that's it. Thanks, Sonal.
Thank you, Shashwat. And thank you everyone for sticking around.